You take a diagonal, you cut zero off the line. Yes. Unless it's not equal to, then the determinant is the product. Okay, for Poisson process, the correlation all the row keys are product. So you view it as identity. So you ensure your kernel gives as identity. Poisson. Because the row keys become product, right? Yeah. And then it's a bit too much because it's spending time. Sum of all the points. Yeah. And part relation. Directly giving the density. Density. K point density. Yeah. Yeah. Those are determinants. For Poisson, it should be products of the time. Determinant of products of the time. Needed to be a part of the time. Which means you put your kernel level all of that kernel zero. Oh, actually, operator. Yeah. Yeah. K x1 is 0. Unless everywhere except y. And your measure is not accounted. Then it is 0. Right? So the operator is. It's not really making sense with the integral stuff. Yeah. You have to in the distribution. So some of the things they use the inverse operator. Correct. Because they lack mass, you won't have densities for it. Yeah. Next. लैब प्रोजेक्ट के बाद रिसोर्स रहा one process is that the solution will be evolving in time first is parallel and the string is and the point opens a goal. Okay, so welcome everybody for the last talk of the day, and we are happy to have Leslie joining us from Madrid. So he'll be talking about determinantal point process, but in higher complex dimension. Over to you, Leslie.
Okay, so first let me start by thanking the organization for giving me the opportunity to give this talk. Let me also start by apologizing that I couldn't be here in person. I would have really liked to come, but unfortunately it wasn't possible. But I'm still grateful that that I got the opportunity to give my talk online. So I will talk about high-dimensional determinantal point processes and in particular their edge behavior. So some of the things I'm going to tell now were already said in Jordi's talk, but okay, repetition is good every now and then. So let's start with a point process. So in our case, we will just consider them on either R to the D or C to the D. And then a point process is a probability measure on the set of all configurations of F. So configurations are the subsets that don't have accumulation points. So there is a more formal definition that you saw in Jordi's talk, but okay, for our purposes, when you are in R to the D or C to the D, this is the definition we use. And a point process is called an endpoint process if with probability 1, its configurations have endpoints. And a prototypical example of this is a random matrix. When you consider a random n by n matrix, and if the distribution is not too crazy, then with probability 1, there will be exactly n distinct eigenvalues. So the eigenvalues are then an example of an endpoint process. So let's look at one of the simplest examples of such a random matrix model. So this is a model that that Jordi skipped, but I will introduce it now. So it's the Ginebra ensemble. So in this ensemble, you consider n by n complex matrices whose entries are distributed as follows. So they are distributed by this formula here. You can see my cursor, by the way, right? I hope.
Yes.
Okay, good. So this Zn is just some normalization constant. But then here we have e to the minus the trace of some function, some potential, if you will. And this potential is just quadratic. So in our case, it means that it's given by m dagger m, so the complex conjugate and transpose of m times m. And dmn is just the product of Lebesgue measures of all the independent real and imaginary components. And if you think about it, if you rewrite this trace of v of m, then actually you see that this means that all the entries are distributed by Gaussian distributions with mean 0 and unit variance. So this is really one of the most basic models that you can consider. So all the entries are just Gaussian distributed. All right, so it was introduced by Ginebra in '65. I'm putting here between parentheses complex Ginebra ensemble because he also introduced a real and symplectic version of this model, but we will only focus on the complex Ginebra ensemble. And he essentially introduced this as the unconstrained version of the Gaussian unitary ensemble, which is one of the most famous random matrix models. So this is defined as follows. It's very similar to the definition of the Ginebra ensemble, but now it is assumed that the matrices that we consider are Hermitian. There must be some Hermitian symmetry for these matrices. So the definition is almost the same, as you can see, but now this DMN is different because there are fewer independent components of these matrices. And the reason that that this Hermitian symmetry is considered is that in that case, you know that all the eigenvalues are real. And that is originally how random matrix theory really took off, at least in physics. So several physicists like Wigner, Dyson, and Mehta in the 50s and 60s, they tried to describe certain disordered models, in particular heavy nuclei. And the assumption was that these eigenvalues give you an idea of the energy spectrum, the energy levels of these heavy nuclei. And of course, then these eigenvalues have to be real. So this is why the focus initially was on these Hermitian random matrix models. Now, the Ginebra ensemble does not have this Hermitian symmetry. So, so in particular, a big difference between these formation models is that the eigenvalues of the Geneva ensemble live in the plane, right? They live in a complex plane. For this, yeah. So the Geneva ensemble is an example of a so-called non-Hermitian random matrix model. This is because with probability 1, the matrices in this model are non-Hermitian. Now, when Ginebra introduced this model, it was basically out of mathematical curiosity. He didn't really have a physics application in mind. But nowadays, we know that there are many applications of this Ginebra ensemble. It has, for example, a Coulomb gas interpretation. There are also applications in quantum mechanics, quantum chaos, and quantum chromodynamics, to name a few. All right. So let us look at a typical configuration of the Ginebra ensemble. So on the left-hand side here, you see a typical configuration of the Ginebra ensembles, so the eigenvalues of the Ginebra matrix. And then on the right-hand side, what you see there is points dropped with a uniform distribution on the unit disk. And there is some notable difference that you can see. So if you look on the right-hand side, you see there's much more clustering of points. There are much more points that are close together compared to the picture on the left-hand side. And so what you see is that there is a mutual repulsion between the eigenvalues in the Ginebra ensemble, right? So that's okay. And you can also put that into formula. So in Ginebra's initial paper, he derived the joint probability density function of the eigenvalues of the Ginebra ensemble. And what he found is this simple formula that you see here. So if you consider, if you let rho n denote the joint probability density function of the eigenvalues, then it's given by this simple formula here. So Cn is some normalization constant. And here you see a factor with all the mutual distances. A van der Monde factor is what we call that, but okay, that's not so important. And you clearly see that if 2 points are getting close to each other, then the probability density will become close to 0. So this causes this mutual repulsion. Now, there is another way to understand this mutual repulsion, and that was also clear in Jordi's talk already, which is that actually this Geneva ensemble forms a determinantal point process. So what this means is that when we look at the k-point correlation functions, or the joint intensities, it's another name that's being used, then the following thing happens. So if you integrate out n minus k variables of the joint probability density function, okay, multiply it by a combinatorial factor, then you can express this as a determinant of a matrix that is constructed out of just one single function of two variables. This Kn that you see here, which we call the correlation kernel. And this correlation kernel is really a central object, a fundamental object for determinantal point processes. It really characterizes the entire determinantal point process. And in the case of the Geneva ensemble, it has an exceptionally simple form. It's just this Gaussian weight factor here times a sum over some monomials, or products of monomials that you see here. Okay. So what Ginebra also showed in his original paper is that when you look at the average density of points, then this converges to a uniform law. So if you think about this a bit, the density of points is actually given by integrating out n-1 variables. So the 1 point correlation function is actually what gives you the density of particles, right? If you divide that by n, then well, what is left is just the correlation kernel on the diagonal, right? So you have to take the limit of the correlation kernel on the diagonal. And what Ginebra showed is that if you are inside the unit disk, then then this limit will be some constant, 1 over pi. And if you're outside of the closed unit disk, then everything will converge to 0. So there's some uniform law for this average density of points. Right? Actually, the value exactly on the boundary, so on the unit circle, was not in his paper yet, but okay, the limiting value is just the average between the inside value and the outside value. Okay, so in general, the set on which the eigenvalues accumulate, we call the droplet. That's the terminology. So in our case, the droplet is just the closed unit disk. And then the interior of the droplet is what we call the bulk. So that is, in our case, the open unit disk. And the boundary we usually call the edge. So that's, in our case, the unit circle. Now, what we are often interested in random matrices is so-called scaling limits, or local scaling limits. So I'm giving you the example of a bulk scaling limit. So we're taking a point in the bulk. So in our case, the bulk is the open unit disk. As we take a point z with modulus smaller than 1, and then we rescale our variables around z in this way, you see here. So z plus u over square root n and z plus v over square root n. And then it turns out that we get, well, this particular limit here. So this 1 over pi times this exponential. Now, this limit that you find on the right-hand side is actually a well-known limit. And in particular, it is known that it is universal. So what I mean by that is the following. I mean that you encounter this same limit in many different types of models. So there's also a name for this limit that we use. It's called the Genebra kernel, or sometimes it's called the infinite Genebra kernel. And it turns out that it appears in many other models. So some examples are what we call random normal matrices, also independent entry matrices, and also more generally, it appears in determinantal point processes on complex manifolds. Okay, I'm omitting references here, but okay. So there is a relatively easy way to see that you get this limiting behavior in the bulk. So under the condition that you see here, so this 1 minus z w bar, the distance has to be bigger than some constant, and okay, we also have to stay away from the origin by some distance. But then the following general asymptotic formula is valid for the kernel that you see here. And in particular, if you plug in this choice for z and w, so this z plus u over square root n and z plus v over square root n, then you kind of already see this Genebra kernel appearing. This first term will turn into a Genebra kernel, and this second term will not be dominant. It will tend to 0. Right? Now, actually, as you might have guessed from the title of my talk, actually our focus will be on the edge. So we are interested in the boundary behavior. So in the case of the Genebra ensemble, we take z and w exactly on the unit circle, which is the edge. And then it turns out that it's actually not the first term here that dominates, but it's actually this second term that dominates. And what remains, the dominant behavior, is actually this. So there's also a much more general result in this direction by Ameur and Kronwall for random normal matrices that show that there's always such an edge behavior for these type of models. And in particular, this edge term, so this second term here, it turns out that this gives a non-negligible contribution to the variance of linear statistics. So as you saw in Jordi's talk, there is a way to express the variance in terms of an integral over that involves the correlation kernel, and you see that this term, this edge term here, is exactly what causes here this second term. So this double integral over the boundary, over the edge. Okay, so this was originally proved by Ryder and Virac. And later in greater generality by Ameur, Hedemalm, and Makarov. Now I should say that for this behavior on the edge, we made a tacit assumption, which is that Z and W do not equal each other. If they do equal each other and they are both on the edge, then actually this first condition here is not satisfied. So this 1 minus ZW bar will be 0, right? Now, in my talk, we will actually be focused on exactly that case, the case where Z and W are on the edge or near the edge, but they are also close to each other. So in that case, this asymptotic behavior is not valid anymore, and we're in a different situation. So for the Geneva ensemble, it is known what happens then.
Leslie, just one.
Yes.
In the expression for variance, there is no end dependence, is there?
That's a good point. Yes, sorry, this should have said the limit of n going to infinity of this variance. Yes, sorry, yeah. So if you consider the variance of this linear statistic and you let n tend to infinity, then this is the formula you get. That there should have been a limit n going to infinity in front of this here, I forgot. Okay. Okay, so let me continue then with, with the following scaling limit. We call this an edge scaling limit. So here we take a point on the edge, so Z on the unit circle, and we rescale our coordinates in the following way. So we add a u over square root n times z and a v over square root n times z. And then it turns out that we get the following limiting kernel. So here, this denotes the complementary error function. And this is also a universal kernel. So it has a name, the Vadeva plasma kernel. Sometimes it's also just called the error function kernel. And so we know that this kernel is universal. So in particular, Tao and Wu proved it for independent entry matrices that have to satisfy some four-moment condition. This was later improved by Cipolloni, Erdős, and Schröder, who showed that that the fourth moment condition can be relaxed. But our main focus will be the situation that Heidenbaum and Venman consider. So they show that the kernel is universal within the model of random normal matrices. At this point, I'm going to explain to you what random normal matrices are. So the definition is very similar to the case of the Geneva ensemble. So in a Geneva ensemble, remember we had n times n complex matrices, and then the entries were distributed according to this formula here. The only difference now is that our potential V will not be quadratic, but it can just be a general potential. And this class of models is what we call random normal matrices. Okay. Of course, this V does have to satisfy some regularity and growth conditions to assure that that everything is actually normalizable. But okay, apart from that, we can consider general potentials. So here we can also find a relatively simple formula for the eigenvalues. So we see that that we get a formula that is almost the same as for the Geneva ensemble, except now the last factor is not e to the minus n z modulus squared, but it's just it contains this potential, right? But already from this formula, it is clear that there is also some mutual repulsion going on between the points. And in particular, the eigenvalues also form a determinantal point process. So in general, the k-point correlation functions can be expressed through a determinant of a matrix that's constructed with a correlation kernel. But now the correlation kernel is less explicit than before, but it is constructed with certain, we call them planar orthogonal polynomials. So the correlation kernel is given by the square root of this product of weights. And then there is this sum over a product of orthogonal polynomials. And we call these planar orthogonal polynomials because they have to they have to satisfy these orthogonality conditions that you see here with this weight that this weight omega z is e to the minus n v of z. And we call them planar orthogonal polynomials because we are integrating here over the complex plane. Okay, and in the case of the Geneva ensemble, these planar orthogonal polynomials are just monomials multiplied by some constant factor, right? So that explains why before we had this particular form for the correlation kernel, right? They're just monomials here. All right. So you can show that under general conditions, if you look at the eigenvalues of these random normal matrices, then they will also accumulate on some droplet. So before the droplet was the closed unit disk, but in general, it doesn't have to be the closed unit disk, it can be something else. But under certain general conditions, at least it will be some compact subset of C. And in particular, if we look at the average density of points, then that converges, in the bulk to this formula here. So this 1/2 pi times the Laplacian of the potential. So before we had a quadratic potential. So that means that indeed we get a uniform law because then this is just constant. But in general, this is what you get, this Laplacian of the potential. And then, okay, outside the droplet, of course, we get 0 then. Okay, so what Hedemann and Wendland proved is the following. So they consider this situation of random normal matrices, and they and they assume that V satisfies a condition that they call one admissibility. It's actually a condition consisting of 5 subconditions that look a little complicated, but are actually quite natural when you think about it. And under these conditions, they show that if you take a point on the boundary of the droplet, so on the edge, and you let this n denote the outward unit normal vector at z on the boundary, then you have the following scaling limit. So if you take your local coordinates around z in the following way here, so it involves the Laplacian of the potential, and you have to rescale by a factor square root of n. And you use here the outward unit normal vector in this way. Then you will find this Fadeva plasma kernel that we saw before. I'm using here an equality sign with 3 bars because this is actually true up to some, well, let's say unimportant factors. They're unimportant in the sense that when you calculate the determinant expressing these joint intensities, actually these factors don't matter. The determinant is invariant under these factors. So they don't matter for the actual determinantal point process, right? But to avoid giving these factors explicitly, I just use this notation with 3 bars. But the point is they essentially proved that the Fadeva plasma kernel is universal within the model of random normal matrices. Okay, so we will consider determinantal point processes in higher dimension. We'll consider them on C to the D. In this case, there is no, for as far as I know, no connection with random matrix theory anymore. At least if there is, it isn't obvious. So what will we consider? So our starting point will be the correlation kernel. So we define a correlation kernel as follows. So it all starts with a certain multivariate weight, which is defined on C to the D. And then, okay, and the correlation kernel is defined as the square root of these weight factors times a sum over a product of orthogonal polynomials. But in this case, they are multivariate orthogonal polynomials. So they have to satisfy these orthogonality conditions that you see here. And in particular here, we are integrating over C to the D. And this Jn here is an index set. And it's such that when you consider the set of all these multivariate orthogonal polynomials, then this forms a basis of the space of all polynomials of total degree smaller than n. So as you might notice, if you take D as 1, this is just the exact same definition as for random normal matrices, because then the index set just contains the indices from 0 to n minus 1. Right? Okay, so it's really a generalization in a way of these random normal matrix models. Even though for D is bigger than 1, the connection with random matrices is gone. Okay, so you can show that well, all the conditions of a determinantal point processes are satisfied. You can also find out the total number of points. For D is 1, the total number of points is just n. But in general, for D bigger than 1, the total number of points is actually given by this binomial coefficient here, which I think behaves something like something of the order n to the D, I think. Well, what it means is that when you look at the k-point correlation function, so these joint intensities, then when you integrate out n minus k variables, you get this determinant of this matrix constructed with the correlation kernel as defined here. Okay. So there's also another interpretation. I believe Jordi talked about this a bit also. If you consider this correlation kernel, but without this square root of weight factors, then this expression is known as the Bergman kernel. So it's a Bergman kernel of the Hilbert space of for all polynomials of total degree smaller than n, with respect to the following weighted norm. What this means is that if you take one of these polynomials, p, j, w, and you multiply it with this Bergman kernel and integrate over it, then this will give you the same polynomial back. So it's a projection operator. Okay. So one particular person who studied these type of models before is Berman, not Bergman, Berman. They are two different people. So Berman studied Bergman kernels, or more generally, determinantal point processes on C to the D. And actually, he considered a much more general situation. So he considered the situation of complex manifolds that have a complex line bundle defined on them. And then he constructed this Bergman kernel in terms of the global sections. But I'm not, okay, I'm considering the case that we're just on C to the D, the much simpler case. So what Berman could prove is that well, under fairly general conditions, he could show that here there is also a droplet in a sense. So if you look at the average density of points of these models, then this will also converge on some compact subset of C to the D to some measure. The Monga Ampere measure, but okay, that's the name. So in a later paper, he also found a universal bulk limit, a bulk scaling limit. So if you look at this correlation kernel and you rescale your coordinates in the bulk in just the right way, then you actually find this limiting kernel that you see here. It's actually not the Geneva kernel because remember now that U and V are in C to the D. But if you think about it, this limiting kernel is actually a factorization in Geneva kernels. Right? Because this dot product here you can write as a sum of D terms, and you can do the same with the norm of U squared and the norm of V squared, and then okay, you get D factors of Geneva kernels. Okay, but of course our focus is the case of the edge. So in this particular paper, he says that he postpones the more challenging question of what happens on the edge. So what I will show in this talk is what happens for a particular class of models. So I will consider a particular, well, elliptic class is what I call it, for reasons that will become clear shortly. So yeah, so we investigate the multivariate weights of the following form. So they are products of planar weights. And these planar weights are defined as follows. So they're exponentially varying. So they're of the form e to the minus n v of z. And now we take an explicit choice for v. So we consider the potential vz, which is given by z modulus squared minus tau times the real part of z squared. So this depends on a parameter tau, which is 0 or strictly between 0 and 1. And okay, so this describes a system of mutually repelling particles. That's simply because it's a determinantal point process. Well, they are confined to the origin by this external field here. So if you think about this, for d is 1 and tau is 0, this is just the Geneva ensemble that we started with. If you have d is 1 and you take tau strictly between 0 and 1, then we also get a model that is well studied. That's the so-called elliptic Geneva ensemble, which was introduced by Girko in 86. So so the reason that this is called the elliptic Geneva ensemble is as follows. So if you look at the droplet of this model, so if you look at the average density of points and you look at on what set they will accumulate as n tends to infinity, then it turns out that this is an elliptic region. Right? So the eigenvalues accumulate on this explicit set here, and this is exactly the formula for an ellipse. Okay, so that's where the name comes from. It's maybe also interesting to note that there really are applications in physics of this particular class that I'm considering. So in the limit that tau goes to 1 of this model, we know that we actually get a determinantal point process in R to the D, which describes non-interacting fermions with harmonic oscillator Hamiltonian, which is quite an interesting model. In a way, you could see it as a d-dimensional version of the GOE. In particular, there are many scaling laws or limits that you find here that are kind of d-dimensional versions of well-known limiting kernels that we know from the GOE. In particular, I think Jordi mentioned this kernel by the Bessel point process. That is something that you find in these models. Okay, now for tau is 0, it is known that this describes non-interacting fermions in a rotating trap, where the rotation has a speed that is near some critical speed, and then to good approximation, okay, it is described by this model. So for D is 1, that was shown by these 3 physicists, but this interpretation is also valid for D bigger than 1. It may be also interesting to mention that these situations can actually be done experimentally. So this first model in R to the D can be done experimentally for D smaller than or equal than 3. And this second model can be done for DS1 experimentally. All right. So let us look at the explicit form of the correlation kernel. So when tau is 0, so when we have this multivariate weight, where we have the norm of z squared here, then the correlation kernel is given by this formula here. Well, the reason that we get monomials here, a product of monomials, is as follows. So when you have a multivariate weight that decomposes as a product of planar weights, then it actually means that the multivariate orthogonal polynomial also decompose as planar orthogonal polynomials. So that means that we just have to use the planar orthogonal polynomials of the Geneva ensemble, which we know are monomials. So that's why we get this particular formula for the correlation kernel. And this notation here, J modulus is smaller than n, indicates that we are summing over all multi-indices such that the sum of the components is smaller than n. Now you can do something similar for the case that tau is strictly between 0 and 1. So then it turns out that actually the planar orthogonal polynomials that you use are Hermite polynomials, so they're defined by this formula here, or V-scaled Hermite polynomials, maybe I should say. But the point is that in both situations, the multivariate orthogonal polynomials and the kernel are explicit. All right. So together with some of my colleagues, we found out the explicit form of the droplet here. So you can derive that that when you look at the average density of points, these points will accumulate on the following set here. So the average density of points will converge to a uniform law on this set here, on this droplet. And this formula here that describes the droplet is the formula for a 2D dimensional hyperellipsoid. So this is also why I call this class elliptic, because of this elliptic structure of the droplets that you find. So in a way, Berman's paper tells us that this must happen, that you get this uniform law on a particular droplet, but his paper does not tell you what the droplet is exactly. So that's what we showed for this model. And you can also, we also found a bulk limit, which agrees with the result of Berman. So if you take a point inside the bulk and you rescale your coordinates in just the right way, then you will find this factorization in Geneva kernels that we saw before, up to some unimportant factors that drop out when calculating determinants. Well, as I said, to some extent, you can deduce this from this paper by Berman, this 2018 paper, except that, okay, you don't know in advance what the explicit form of the droplet is. So this is, okay, this is about the bulk, but let's now move to the edge. So there the result is as follows. So we consider this elliptic model with this multivariate weight for this elliptic class. And the result depends on some constant, nu, that has to be between 0 and 1/6. And okay, the situation is as follows. We take a point Z on the edge, so on the boundary of this hyperellipsoid. Again, we use in our result the outward unit normal vector on the edge at this point Z. And then the result is as follows. There exist continuous unimodular functions Cn, such that we have the following asymptotic behavior. These continuous unimodular functions are actually the unimportant factors I've been mentioning. And this is the asymptotic behavior that we get. Here, this Geneva factor here, I just put on this side of the equation to save space, but okay. But this is what we get. We get some complementary error function behavior. And this asymptotic behavior that you see here is uniform for Z on the edge, and U and V have to satisfy this growth condition. So this is where this constant nu comes in. So U and V are allowed to grow, but not too fast. Okay, now this result in a way depends on the geometry of the droplet. When we look at this as this asymptotic formula, we still have this outward unit normal vector. And there's a way to get rid of this dependence on the geometry of the droplet. And then you have to actually use the outward unit normal vector in the following way. So this is a direct consequence. So if we take the correlation kernel, and now we rescale around this point z on the edge in the following way. So here we are using the outward unit normal vector. And now u and v are not in c to the d, but they're in c. Then it's a direct consequence that you get this limiting kernel that you see here. So you should recognize that this is actually just the Fadeva plasma kernel from before. So this was a bit of a surprise to me. So I expected when I started investigating this model to find something with a complementary error function behavior in there. But to really find the same kernel that you also find in DS1 was somewhat of a surprise to me. So for as far as I know, the Fadeva plasma kernel has not appeared before in a higher dimensional model. But there are related results that that to some extent have appeared in other models before, and that's the case where we consider well, the diagonal case, where we consider the case that u and v are equal. If you remember, when you take u and v equal here, that actually describes the density of points, right? So the next result is as follows. Setup is exactly the same as before, but now we are going to consider the correlation kernel on a diagonal, which is to say we consider the average density of points. And we are going to rescale around z in the following way. So we take z plus lambda over square root n times the unit normal vector at z. And then we get the following. So we get this complementary error function behavior that you see here. And then there are subleading terms of the following form. And this behavior is uniform for z on the edge. And lambda satisfying this growth condition, so depending on this constant mu. And this kappa is a function that's explicitly given like this. So this kappa that you see over here and over here. And similar results were derived by Brazen, Singer, and Zeldich and Zhao for certain, well, somewhat different higher dimensional models in differential geometry. So they considered certain partial Bergman kernels, and then when they look at the average density of points, they get this, at least to the leading order, they could find this complementary error function behavior. There's also a question, which is whether there is some geometric interpretation for this function kappa here. The reason I'm saying this is a result by Rieser and Lee. So Rieser and Lee considered the case where D is 1, so the case of the elliptic Ginebra ensemble. And they could show the following. So again, we're in the same situation as before, just in D is 1. And they could show that if you look at the average density of points and you rescale around a point in the edge, then you get this, well, this same complementary error function behavior plus some subleading terms. And in particular, they could show that this kappa in their formulas was actually the curvature of the ellipse in Z. So it's interesting whether there's also some geometric interpretation in D bigger than 1. All right. So let me see how much time do I have left. Yeah, I could go quickly over. I will sketch a bit how you can prove these results. So the way to prove this is by a steepest descent analysis, albeit a bit of an unusual steepest descent analysis. So it's probably best to illustrate it for tau is 0 first. So if we take this correlation kernel for tau is 0, so remember that's that's this one, this correlation kernel here, then you can find a single integral representation for this kernel. So so we can express the kernel as this this Gaussian vector times the following integral here. So it's a contour integral where gamma 0 is a small loop around 0 in positive direction. And this function f of s is relatively simple. It's given by z dot w s minus the logarithm of s. And this is nice, of course, because it has a form that's suitable for steepest descent analysis. So the way to prove this is as follows. Let us look at the term in the middle here, sandwiched between these equality signs. So this term here, 1 minus s to the minus n divided by 1 minus s to the minus 1, you can write as a geometric series with n terms, right? And if you think about it, the residue theorem tells you that that means that you will get all the terms of e to the z dot ws, where s doesn't have a power higher than n minus 1, right? Now, this e to the z dot ws, you can actually write as a product. It decomposes as a product of d factors. And these d factors, if you write down the power series, then you see that if you consider all the terms that you get with s up to power n minus 1, you get exactly these terms, right? So that's how you go from here to here, or well, maybe from here to here. Now to get to this step, the second step, what you do, well, since gamma 0 is a small loop around 0, it doesn't enclose 1. So there's a pole here at s is 1, but it's not enclosed, which essentially means that we can throw away this 1 here. And that's how you get to this integral over here. Now, at this point, okay, we have to reinstate a factor square root of n. And we can write this s to the minus n as e to the minus n log of s. And then you see this function f emerging. Then you get this function f that is right over here. Right? Okay, and okay, you have to reinstate the weight factors, and then that is how you prove this identity. Okay, so for tau strictly between 0 and 1, you can do something similar. I won't go into every detail here, but you can use the so-called Mailer kernel formula to derive a result in similar spirit. So here it turns out that it has the following single integral representation that depends on, well, z plus and z minus, which are defined, which depend in a certain way on z and w. And in particular, the integral that is involved here is of the following form. So again, there is a small loop around 0 with positive orientation. But here, this function f is a little bit more complicated now. It takes the following form. Still, the steepest descent analysis is doable. It's not straightforward, but it is doable also for this case to find all the saddle points and things like that. Okay. So what we really want to do when we look at these edge scaling limits is we want to replace z and w by these rescalings around z, right? Where z is a point on the edge. Now, for the case tau is 0, it's quite easy to see that that one of the saddle points is z dot w inverse, right? If you take the derivative here, you get z dot w minus 1 over s. So the saddle point is given by z dot w inverse. And if you then perform this substitution here, you see that in a large n limit, the saddle point will behave like this. So it will be close to 1. Now that is a bit of an issue, because if you remember, there's also a pole at s is 1. So it's a bit of a complicated situation where in the large n limit, the saddle point and the pole will coalesce. Now, now in the case that tau is strictly between 0 and 1, it turns out there are in general 4 saddle points, at least when we're on the edge. And one of these saddle points will also coalesce with the pole of the integral that's involved here. So, so here we had this integral, and there's a pole at S is tau. And here also the saddle point will coalesce with the pole. So the main question is, okay, how do you perform a steepest descent analysis when the saddle point coalesces with a pole? So there is a little lemma for this. Well, we'll get to in a moment. So the first step is to use an explicit conformal map to essentially make this function f quadratic. So you can find a conformal map explicitly such that this is true. And then if you perform a substitution of integration variables, you can actually turn your integrals into the following situations that are easier because now the function that you have here is just purely quadratic. So yeah, so you get an integral of this form, plus some steepest descent integral that is doable. That's not difficult. But here it is still true that the saddle point coalesces with the pole in a large n limit. So if you think about this, if you take S is 1 in this formula here, then well, S0 will approach 1 as n tends to infinity. So since the left-hand side will approach 0, that means that phi of 1 will also approach 0 as n tends to infinity. But it's a much easier situation now because everything is just, okay, nice functions, right? Okay, and something similar also happens in the case that tau is strictly between 0 and 1. And now there is a little lemma on how you can continue. So if you consider any two integration bounds, L1 and L2, and you consider some number p in a compact subset of C such that the real part is between these integration bounds, then it turns out that you get the following asymptotic behavior. So you can show that this integral is actually given by, well, this factor here, plus some O term. And this factor, of course, is very nice because it shows you exactly how this complementary error function rolls out of our formulas. Right? So yeah, I think I have time to go through a proof here. So, okay, so you may essentially replace L1 and L2 by minus t and t. You can show that that can all be absorbed in this O term. And then by a contour integration, you can show that this integral is actually given by pi I e to the minus n p squared minus some principal value integral. The way to show this is to use the following contour. So our original integral is going from minus t to t. And you can show that the integrals over the vertical line segments will go to 0. This small semicircle here will produce half a residue. That's exactly this term. And then what remains when you take the limit t to infinity and the limit epsilon to 0 is just this principal value integral. Okay. All right. And what you do then to calculate this principal value integral is the following. So, so this e to the minus n t plus p squared, we can write as e to the minus n p squared times e to the minus n t squared. And then we have one remaining factor, which is e to the minus n 2tp. And that we are going to write as a power series. And if you think about that for a moment, you notice that actually only the odd indexed powers can survive. Because the even index powers that will contribute 0 because of this symmetry or antisymmetry, maybe I should say, of the other factors in the integral, right? So we only have to consider the odd index terms. Now, what we do then is we interchange the integration and summation. And okay, we get integrals that are just doable. You can write them as you can identify them as with in terms of the gamma function, and then this is what you get. Then you can use the Legendre duplication formula to get it in a different form. And this form is exactly the Taylor series of the error function, right? And now together with this this half residue from before, that will actually produce a complementary error function. So that's how you prove this lemma. Okay, so this was to give you a little sketch on how you prove these formulas. So let me then end the talk with some concluding remarks. So we showed that you find this Fadeva plasma kernel for determinantal point process in C to the D for this particular class of weights. Now, since it's an entire class of weights, I think that's strong evidence that probably this Fadeva plasma kernel is universal also for these, for certain determinantal point processes on C to the D. And one of the questions I'm trying to answer is, well, what then characterizes multivariate weights where you find the Fadeva plasma kernel as an actual scaling limit? Okay, so that's where I will stop, and I thank you for your attention.
Any question, comments? Okay, one I had was, I mean, these are weighted Bergman kernels, the determinantal process I mentioned. Are there other possible kernels of interest, or is there anything else?
So I have not been working on those. I mean, in higher dimension, yes. I mean, Jordi gave several examples. For example, on the sphere in higher dimensions. But yeah, in particular, I mean, one of the most general settings I've seen is in this paper by Behrman, where he considers complex manifolds, but there he still considers Behrman kernels in a way. So yeah, different than Behrman kernels, I'm not sure. I mean, I think you can always kind of no, those are still Behrman kernels. No, I think this is my answer. Yeah.
Thanks.
And about this last thing you mentioned, do you have any? Yeah, this universality question. So do you have any advance on this or not yet?
Yes. So so there is another model where you consider generalized Laguerre polynomials. They have a formula similar to this Mailer kernel formula that I mentioned before, the so-called Hardy-Hill formula. And you can do something similar, something in the same spirit as the approach that I used for this model. And some preliminary calculations show that you probably find something similar. Yeah, other than that, okay, I've also teamed up with another researcher that that is more familiar with general models of this case. Actually, that's Van Man from one of these theorems. So yeah, so we're trying to find out how to do this in higher dimensions.
Yeah.
So for the droplets, you have a different scaling or the same scaling at the cusps and other places?
Sorry, I couldn't hear the question.
For the droplets, do you have a different scaling at the cusps or?
I'm not sure that I understand what you mean by the cusps.
So the droplet is smooth. The boundary has no cusps.
Not for the model I considered, I think. Okay. No.
I had a question that's possibly related to the question that was just asked. So the scaling factor of square root n, that basically has to do with the fact that your domains are all have smooth boundary and they're, I guess, strongly convex, right?
Sorry, your volume is a little low. I couldn't hear the question.
Just 1 second. Let me see if I can make this slightly better. Can you hear me better now?
Yes. Yes.
Yeah. This is related to the question that was just asked. So in your scaling limits, the power of n, the square root n you have, that has to do with the fact that the domains have smooth boundary and they are, I guess, strongly convex, at least at most points.
Oh, I don't think I can.
The question is why square root n? Is there like an abstract reason why we should expect that?
Oh, I would have to think about that. I mean, for the models I considered, I could just identify that was the power that worked. But if there is a deeper reason to expect that, let me think about that. No, I don't think I could give you an answer.
Okay, thank you.
Okay.
Okay, so if no other question, let's thank Leslie.